So hello everybody, we are back again to our plasma class, and what we are doing today is we'll be starting the plasma fluid model. So we are gradually passing from this plasma orbit theory, then kinetic theory, and then fluid model. So before entering into fluid model, earlier what we are discussing, let us recapitulate, and little bit was left in that. I will finish that and then I will enter into this fluid model. So what we are doing earlier, that damping of this electrostatic waves, Langmuir waves damping. So what we found, that whenever a high frequency electrostatic wave tries to propagate through a plasma, the particles in the plasma interact with the wave, and sometimes they try to accelerate the wave, sometimes they try to decelerate the waves. How it is? Because you know that particles are having distribution of velocity, not a particular fixed velocity. They are having a distribution, and you know that for the particular kind of distribution, assuming a Maxwellian, we found that the number of particles which are having your velocity more than the velocity of the wave is usually less than the number of particles which are having velocity less than the wave. So number of particles are having velocity less than the wave velocity is more always. So those particles, what they are doing, they are trying to decelerate the waves, and that's how the wave is getting damped. Those particles which are having higher velocity, they are definitely trying to accelerate, but their number is less. So that is how the ultimately the wave is getting damped. Now our question was there, whether is it possible? Is it possible to amplify instead of damping? Then we found that sometimes it is possible. Sometimes it's possible to amplify the wave using the same mechanism, artificially creating a modified distribution of the particle velocities. So suppose we get a modified distribution like the one that we have shown in the figure here. So what it is, instead of having a symmetric profile, it is having a bump on the right hand side. And if we are able to inject, a wave for which the phase velocity omega pi k falls in this rising part, then you can see the number of particles for this particular wave having velocity more than omega pi k is more. Here it comes here. Then the particles which are having velocity less than omega pi k here. So because the number of particles more than the wave velocity is more compared to those which are having less velocity than the wave velocity, so the wave gains energy from the energetic particles. So that's how the wave can be amplified if this kind of modified distribution exists, and that can be created by injecting some beam and of a particular distribution, so that you get the modified distribution in this form. So if it is possible to have this kind of distribution, and if we are injecting a wave having phase velocity omega k which falls in the rising part of the modified distribution here, then it can be amplified as well using the same mechanism by transporting energy from the particles to the wave. So that is how we can amplify sometimes the electrostatic waves in certain systems. So coming back to the fluid model, as I told you earlier that plasma kinetic theory gives the exact evolution of position and velocity of the with time for each species, and that includes the collisions as well. Okay. Now what happens, because each and every species is addressed in this kinetic theory model, their position and velocity are of interest. Sometimes we are actually not interested in so much of information. As I told you that, for example, a glass of water, you know that the number of molecules are moving here and there. All of them are having a distribution of velocities. Different molecules have different velocities, and we are interested only in the how many total number of molecules present in the glass water. So we are not interested which molecule is moving at what speed in the water in the glass. So we are interested in drinking the water only. So what to do with the velocity of the individual molecules inside that? Same thing actually, we are interested in this kind of behavior for pipe flow or for any fluid flow kind of thing. So essentially what we are not interested in, we are not interested in the particular distribution of velocities. We are interested in only the total number of particles in the configuration space. So if it is so, then we can integrate the Boltzmann kinetic equation in the velocity space. Then what we will be left with? We will be left with the only physical space which is having the dimension in x, y and z, and that is evolving with time. So this is essentially the fluid model from 6 plus 1 dimensional kinetic theory model, 6 dimensional space, and one time we describe the equation there in kinetic theory model in this space. Therefrom we are integrating over the velocities and we are arriving at the description of the system in physical space having 3 spatial coordinates, and we are starting the evolution of that with time. So the description is essentially in 3 plus 1 dimension. So that is the fluid model. So we are now entering into the fluid model description of plasma. Now you know that most of the plasmas are basically having this electrons, ions and neutrals. Now as I have described in the beginning classes that ions, because they can respond to the electric field, they can respond in a different manner compared to the neutrals. Neutrals cannot respond to the electric field. They gain energy from the electric field via the collision of the ions and electrons, which are basically influenced by the electric field. So they get energy from the electric field, then they collide with the neutrals and the neutrals gain energy. So in such system, basically you should consider the plasma as a multi-fluid system. One is electron fluid, one is your ion fluid, one is neutral, and maybe possible there are multiple ionized states, each of which are behaving in a different manner. But handling those systems having multi-fluid, nowadays people are doing that, but for a simplified model which can give you sufficient information to understand your system, 2 fluid model is sufficient. Here what we are doing, we are considering plasma as a fluid. One is your electron fluid and one is your ion fluid. Rather, in 2 fluid model we consider electron as one fluid and rest of the heavy species as another fluid. So electrons, because they can respond very fast to the electric field and gain energy, so they initially receive the energy, and through collisions they can collide with electrons, ions as well as neutrals. So the transfer of energy from the ions to the neutrals and your ions acts more or less in a similar manner, although the electrons cannot act through the long range Coulomb force with the neutrals, but it can do so with the ions. Basically ions and neutrals, they stay at almost similar energy, and we can characterize those those fluid which are heavier species in the plasma as by one temperature Th. So H corresponds to heavy and T corresponds to temperature. So apart from electrons, rest of the fluid is heavy species fluid, and that is characterized by one temperature, that is TH. On the other hand, this electron fluid, which is having some temperature TE, which is much greater than, usually much greater than the heavy species temperature. So what essentially we are discussing, plasma as a two interpenetrating fluids. One is electron fluid and one is heavy species fluid. If you consider it is a fully ionized plasma, then it is ion fluid and electron fluid. So in this case, what will define that total number of particles species of species S per unit volume as integration over velocity, then fxbt, that is the distribution function. So you are integrating over the velocity, so you are getting the number of particles per unit volume, that is the number density. And velocity of the fluid element is defined as like this, is equal to 1 by ns. So you are averaging and then integration of dv and v, and this is the distribution function. So that is how you are speaking about the velocity of a fluid element. Now, in this fluid model, we arrived at the different conservation equations, but just by taking moment. Moment means, you know, that it is mathematical moment. So you will be dealing in a much explicit manner in the later classes. So in this model, what we are doing, we are integrating over the velocity space. So information on velocity distribution of individual species are completely lost. So things that may happen in velocity space, like the Landau damping. Here, this kind of phenomena may not be reflected in the fluid model. So now, finally, what we are having? We are having a description of the plasma in three-dimensional spaces, three spatial coordinates and time, and no velocity information is of individual species is available in this model. So the point we must remember to study this fluid model, that total number of species S per unit volume at some point x is calculated as nxt is equal to integration over the velocity space of the distribution function. And the velocity of fluid element, how we are defining, this is the Vsxt is equal to 1 by ns. That ns you have just got in the upper expression. Then you are integrating the distribution function and multiplying by velocity and integrating over the velocity space. So this is how you are getting the velocity of the fluid element, and we are getting different conservation equations from this model when we are taking the various moments of the plasma kinetic equation. When you are taking zeroth order moment, we will get the mass conservation equation. When we get the first order moment, we will get the momentum conservation equation, and when we take the second order moment, we get the energy conservation equation. So what we will do to give just a flavor of how these conservation equations can be derived for a system in thermal and non-thermal plasma, we will do derivation of this mass conservation equation. We will do some derivation of the momentum conservation equation, but as we move on taking higher order moments, then the expressions become too much complicated, and you need some tensor physics kind of thing to tackle the mathematical complexity. So what we will do, we will derive the mass conservation equation in a very elaborate manner, so that you can have a feel of how this moment method works for this fluid model. Then we will derive the momentum equation also, but in that case the derivation of the pressure term involves a bit complex mathematics, and we'll just skip that. We'll get into the final expression what one can get from the first order moment. And for the energy conservation equation, we will explain the terms phenomenologically, so that we do have a feel of different mechanism contributing to the system for the energy conservation. So we will do that in elaborate manner, but we will not do the mathematical derivation for the energy conservation equation. Rather, we will focus on each and every term which is there in the energy conservation equation, how they appear, why they appear, and how they influence. So these things we will be starting in the energy conservation equation. So some fundamental definition that we will require for the fluid model. We are assuming two fluids, so one is your electron fluid and one is your ion fluid. Basically, you can understand that we are assuming that it is a fully ionized plasma, and basically we are assuming that is a singly ionized plasma here. So the mass density is mass of electron and number density of electron plus mass of ions and number density of ions. So when you do that, then you obviously get the per unit volume what is the mass. So that is nothing but the mass density. And similarly, when you multiply the number of electrons by the electronic charge, number of ions with the ionic charge, and then you sum up, then you are getting the charge density. Now, center of mass fluid velocity, we define like this. So, this is ion velocity and this is electron velocity, and you are multiplying by mi ni and me ne over here, and then what you are doing, you are dividing by mass density. So this mass density is calculated over here, and that is how you are defining the center of mass fluid velocity. And now you know that current density, this is nothing but J is equal to n e into v. N is the number density, then is the charge, and v is the velocity. Here what we are doing, we are multiplying the number density of ions with the number charge of ions and then velocity of ions. Then we are adding that with the electrons. So we are getting the net current density over here. And the pressure is additive, so it is sum of the electron pressure and the ion pressure. That P is equal to nkt again. So n will be the number density, then k is the Boltzmann constant, and T is the temperature of the electrons. Similarly, you can find out the expression for Pi. So once you know the number density, once you know the temperature, you can estimate the pressure for that particular component in the plasma. So you can always find out the total pressure what is there, and this is how we define the quantities, and we will use this definition in the later derivation that we come across. Now, what we do is start with the plasma kinetic equation. Okay, for the species conservation equation, as I told you, we will be making a very elaborate and exact derivation how we are reaching there. So we start with the plasma kinetic equation as you are seeing here. So it is del Fs del T plus V dot grad x Fs plus this is the acceleration term, and this is grad V and Fs. And on the right hand side we have something which is related to collision, and since it is del Fs del T, all the terms are having the same dimension, so right hand side also giving you some change of the number density with time, and that is due to collision. Now, as we promised that we will now integrate this over the velocity speed, and we will take the zeroth order moment. That is, we are multiplying v to the power 0. Okay, so nothing we are basically multiplying, we are just multiplying by 1, and we are taking an integration. So that is the zeroth order moment, and we are expecting that this zeroth order moment will give us the conservation equation for mass and for charge. So what you are getting from here, you are just integrating del Fs del T, and then we are integrating over v dv. So it is there, and then this is like this, and this comes out like this, and this is coming like this. Now, On the right hand side, what we do have? We have del fs del t collision into dv. Now, what I will explain you in the later slides, that this term, you will see that this is 0, and again this term also is going to be 0. How there? We will make a bit elaborate derivation, and we will show that these terms are actually 0. And if we assume for the timing they are 0, then what we are getting, this is integral of dv and fs xpt. So what it gives actually, this gives the number density of species S. You see that we defined it like that. So nsxt was is the per unit volume number density. So number of particles per unit volume. So that is equal to dv integral of dv fs into xpt. So this is exactly what we have now reached over here. So this is nothing but ns. So what we are getting here, this is del ns by del t. Then this term, there is grad x, and then you are integrating our v, so dv v into fx pt. Now what was that? This dv v fs xbt, and you can see that what we have defined it over here, this is the velocity of the fluid element. So this is integration over this thing and divided by ns. So we are having only this part in the integrand, so we can write this as ns vs. So exactly that is what we are doing over here. So we have put ns vs over here, and that is equated with the dv del fs by del t on the right hand side. So finally what we are getting at the end is del ns del t. Ns is the species density, species of type S, and this is divergence of Vsns equal to integration of dv del fs by del t, and that is collision term. Now I told you that we'll try to find out why that integration, why that is this one actually, why dv e grad v fs that equal to 0. Okay. So since E is not a function of velocity, we can take it out from the integration. So we get actually qs by ms, you take, and this is E over here, and then dv, then grad v into fs. So this gives you fs out from the integral, and your boundaries are minus infinity to plus infinity. You know that fs is symmetric with respect to this velocity, and you are getting this as 0 because fs is 0 at both the ends, at plus infinity and minus infinity. So that's how you are getting this integration as 0. Now why this dv v cross b, the term that we got over here, that is equal to 0. So what the term is, this is dv, then v cross b, then dot grad v and fs. So why this term is 0? Let us try to find out. Now this is integration of v cross b, then grad v fs. So we can write this as v cross bi, then del fs del vi, because this is a dot product kind of thing. Now one interesting thing is that, this is very interesting, that v cross bi doesn't have any vi component. Okay. So you just note it down. See, v cross b is equal to vy bz minus bz by into I. See, this ith component is not having any x over here. It is in terms of y and z, right? So that is why v cross b doesn't have any vi component. Okay. So if that is so, then we can take this term inside this, because it is not having any vi component. So it will remain as it is. So we put it over here and we write it as v cross bi fs by del v del vi, and that is equal to 0. Now if this is so, then what we are getting, this term out, and so we get this term out, and then because fs is 0 at both the limits, plus infinity and minus infinity, and this is coming out from the integration, so we are getting this term as 0, because when you put the limit at both the limits, this quantity fs is 0. So that is giving you the value 0. So that is how this integration dv b cross b dot grad v fs that equal to 0. Now this is fine. So what we have, what we are now left with is this term is 0, this term is 0. So we have got only two terms on the left side, but on the right hand side, this dv del fs del t collision is there. So how to evaluate this term? Because it is collisional term and we are not very aware of what kind of collision is going on there. So this term needs to be carefully evaluated. So what it gives actually, del fs del t is giving the change in number density within the controller due to collisions. Let us assume that this is an elementary volume in the space. So some particles are going inside. Suppose some particles at the bottom and it wants to enter into this region. So you need to increase its exposition. So that is fine. If the particle is traveling, then it can reach over here. But if you want to increase the velocity of that particle, so that the particle is here, velocity is low and it wants to enter here, so you have to increase its velocity. So what will be that? That will be nothing but accelerating the particles. So what is that? Nothing but collisions, because that through collisions only they are getting accelerated or decelerated kind of thing. So some particles which are outside the volume due to lower velocity may get accelerated through collision and increase their velocity and come inside the elementary volume. But the reverse also may happen. So under steady state, it is a good approximation that within this control volume, whatever the number of particles that are coming inside, almost similar number of particles are going out, so that the net number of particles due to this collision, net change in number of particles due to collision within this control volume is nearly 0. Okay, so it is quite a good approximation under steady state to assume that this integration dv del fs del t c is equal to 0. So if we take that, then what we are getting? This is del ns del t plus divergence of v ns, that is equal to 0. So this is true for every species. So this is true for electron species as well as for ion species. So we will be now using this equation to find out whether we can reach to a some conservation equations about the species or about the charge. So we have, what is that? Del ns del t plus divergence of bsns is equal to 0. So the this is giving you the species conservation equation. So for ions, what we are getting? We will put I for S and we are getting this equation. So this is del ni by del t plus divergence of vi ni, that equal to 0. Similarly, for this actually what we are getting, this is the conservation equation for the electrons. So we are getting del ni by del t plus divergence of v ni, that is equal to 0. Now what we do actually, we multiply this by mi on both sides. So this is giving you del mi ni by delta t, and this mi enters here, divergence of mi vi ni, that is equal to 0. And this one we multiply by mi and we get del mi by del ni, del mi ni by del t plus divergence of mi v ni equal to 0. Now what we do, we add these two equations. So this mi ni and this mi ni, they add up, and this mi ni vi and this mi ni v, they add up, and then they become, on the right hand side we get 0. Now you remember that we have defined mass density as mi ni plus mi ni. Yeah? So in our previous class we have defined like this, mi ni plus mi ni. So that is the mass density. So if we use that, then this is the rho m, and similarly the center of mass velocity is V is equal to 1 by rho m mi bi ni plus mi b ne. So what we are getting? So del rho m by del t plus divergence of rho v, that equal to 0 from this equation. So del rho m by delta t plus divergence rho v equal to 0. So this is giving us the mass conservation equation. Okay. So we stop here. In the next class we will be trying to arrive at the charge conservation equation. So thank you so much. We will meet in the next class.